Hi everyone, so in this tutorial we are going to be discussing backward propagation. So this is the progression from the last lesson, so make sure that you go through forward propagation before you come to this lesson. So as we saw, like we're gonna do some recap here. So in the last tutorial session we discussed forward propagation, and this was the dummy training data I used, right? So I selected data sets from the first row, right? And then we started to perform what we call forward propagation. So we performed everything here, and then we end up with this answer here. This was our predicted value, right? So in back propagation, the aim is to update the weights and biases to get the desired output such that the difference between the predicted value and the actual value is minimized, right? So the purpose of backward propagation, so we're gonna move from this value we got using forward propagation, and then we're gonna compare it with the actual value, right? So as we can see, this value right here is the actual value, right? So there are two options to achieve this. We could change each weight bias manually until we get the desired output, right? We could use a method called gradient descent, or in this case there are many methods, right? But then we're gonna choose to use the stochastic gradient descent, right? So what you can do here, since you found out that the value that you got here is not accurate compared to the actual value, so the problem is here is with the weights, right? These weights, all of these weights. So the first option, you would attempt to like change them manually one by one and see and perform all the calculations and see if you get the accurate value here, right? But then as you can see, there is a lot of values that you will have to change, and then it's a combination of values actually, so it's gonna be kind of tricky, to approach this problem by changing weights and biases one by one, right? So the best way to do this, we have to use this method which is called gradient descent. So let's go down. So we have what we call this, so if we choose option 1, then it will take us a long route to reach the desired output. If we go with option 2, it will take us very less time to get to the desired output, right? Because we'll be performing verified computations, right? We'll perform those computations, and then that's gonna help us get to the desired value. There we have to go with option 2. Oh, sorry, I made a mistake here. It's supposed to be, therefore we have to go with option 2, gradient descent, right? Like I explained just now. So taking note of the word gradient, this implies we are dealing with a derivative, right? So you know that if you have done calculus, you know that sometimes we use the derivatives to find the gradient, right? We have to minimize the error by using its parameters to create an expression, right? So we're gonna select what we call a cost function, which is made up of this error, right? The error, we know that it's the difference between the actual value and the predicted value. So we're gonna create an expression made up of all those of each weight that we want to update, right? We are going to make sure that this expression is positive, right? Thus we will know that we will move in the negative direction of this expression down its gradient. We are going to move in this direction until we find minimum value, right? In other words, we are trying to minimize the difference between the predicted value and the actual value, and that difference, we call it an error. So let's first select the cost function. First we're gonna call our predicted value pre, and then we're gonna call our actual value pegged, right? So then, you can use any value you want, but in this case, in this tutorial, make sure that when I speak about pegged or pre, I mention those values. Then our selected cost function is determined by this, right? You see, we have the difference between the predicted value and the actual value squared. Remember, this value, we need to make sure that it's positive, right? Considering the above expression, we will calculate the partial derivative with respect to each weight and bias, right? So it will depend which weight we want to change. Actually, we're gonna change every weight and every bias. We're gonna update, actually. So we're gonna we're gonna compute a partial derivative with respect to that weight or bias. So as you can see here, we want the first thing the first weight we want to update here is weight 7, right? So we're gonna take the cost function. As you can see, we have the cost function, and then we're gonna derive that cost function with respect to W7. This means if I perturb 7, how does that affect the cost? But then this has to be performed for each and every weight or bias. So as we proceed, you remember when we were doing forward propagation, this was the node. So weight 7 was attached to this node, right? And then what happened here, we need to consider which parameters were there, because this predicted value is made up of these 3 parameters, right? So we need to also consider them. So how is this done? So as you can see, we have the cost defined above there, and we have, so we're gonna use the chain rule. We're gonna use the chain rule method. So according to the rules of partial derivatives, so we have the cost we're gonna derive the cost function with respect to weight 7, right? But then you remember this value right here is made up of these 3 values. So this weight 7 is embedded within this parameter, right, for the predicted value. So the only way for us to be able to derive this expression, we will have to go within this expression to be able to derive it with respect to W7. So we cannot directly compute that partial derivative, right, considering only the cost, right? Well, since weight 7 is embedded within here, we will have to say the cost function. If we are looking at here, we'll say that the cost function, the derivative of the cost function with respect to the predicted value multiplied by the derivative of the predicted value with respect to the weight 7, right? So that is how you will be able to find to compute that derivative, right? So we're going to use what we call chain rule. If you're familiar with calculus, you will understand that if we have a function and then we have expressions, so if that means we are, let's say we have a composite function, right? So we have a cost function, and this cost function is composed of the pre-function, right? So we're gonna start with the one that is the major function, and then this pre is more like the composite of that function, right? So we are going to go about from the main function, multiply the derivative of the main function with respect to the chosen variable multiplied by the derivative of that composite expression with respect to that function. Let me repeat that. So we have the main function, which is the cost function, right? Then this cost function is composed of the pre-function, as you can see, right, within the brackets. So if we derive this with respect to W7, W7 is inside the pre is inside the cost function. So we will start deriving the cost function with respect to pre. Why do we choose pre? Is because pre, it has the variable W7, and then that's when we are going to get our answer, right? So let me go down. So we know that pre, from the last tutorial, our pre was defined like this, and then we have our cost, and then now it's time to substitute. So if we derive the cost with respect to W7, or no, with respect to pre, so if we look at the left hand side of the equation, we are going to first compute the derivative of the cost with respect to pre. If we derive cost with respect to pre, this is what we get here. We get 2, and then inside open bracket, pre minus pegged, close bracket, and then we come to pre now. If we derive pre with respect to W7, as we can see here, we will treat all these other parameters as constants, right? The derivative of constant is what? It's 0. So we have this one. We know that if we have a variable, if we derive with respect to that variable, right, and then it is raised to degree 1, and then the only thing that will be left after we derive is the constant attached to that variable, right? So that's how we computed the derivative right there, and then we substituted those values, and then our final answer is going to be negative 78.08, right? That's our final answer right there. So as we proceed, so now we're gonna do the same for weight 8, right? We have pre is the same, we have cost is the same, then now we're gonna, so it's the same, deriving cost with respect to pre, we get 2 open bracket pre minus peg multiplied by p2, because we are going to derive pre with respect to w8, and p2 is the only variable attached to w8, so that's why we only left with p2 there. So that's our product there, and then we proceed to substitute, and then we get our answer there. And then we also do the same with B3, bias number 3. So we're gonna do the same, and then we have pre, you remember, so this one deriving cost with respect to pre, our answer is going to be 2 pre minus 2 open bracket pre minus peg close bracket, and then we're going to multiply that by the derivative of pre with respect to b3. So if you look at pre and then you look at b3, as you can see, the constant attached to b3, it's 1, right? So we're going to be left with 1, that one which is within the brackets. Then we also substitute, and then we get the answer. So we have the gradients of those weights. So what's the next step? So updating the weights and biases, we walk down the cost function in direction of the negative partial derivatives by taking small steps, also known as the learning rate. So this is what we call the learning rate, which is a very important parameter. All right. So we are going to substitute. You remember we have a current weight, right? And then we're gonna substitute the learning rate right there, and then we're gonna substitute this negative 78.08 is the value that we computed above there, these 3 values. So we're gonna substitute those values, and then we're gonna get our answer. And then we're gonna do the same for weight 8 and bias 3, right? So we're gonna get those values right there, right? So we will also have to update other weights, right? So let me check. So what's happening here is that, as you can see here, these were our initial values, right? So we have updated them. We have updated this one, and this one, right? So the next step now, we have to also update these values, right? So what's gonna happen, you're gonna use the same procedure. So we're gonna use the current weight 1, subtract learning rate, multiply by the derivative, the partial derivative, right? So it is the same procedure for all of them, right? And then let's go down. So let's start with weight 1. Now we're gonna update weight 1, right? We are using the same procedure. We're gonna use the same procedure, but things are going to get a little bit different now, because now we are having these values here, and as you can see from the previous steps, we only ended here, but now we are going beyond this node, so we will have to get to the other side, right? So that is gonna take us, it's gonna require us more computations, right? So if I go down, so this is how it's done. we're going to say the derivative of the cost function with respect to weight 1 is equals to, you're actually going backwards, so you're going to say the derivative of the cost function with respect to pre multiply by the derivative of pre with respect to this output 1, right, multiplied by the derivative of this output with respect to weight 1. Let me repeat again. So we're going to say the derivative of the cost function with respect to this parameter, the predicted value here, and then we're going to move again, we're going to multiply, right, we're going to multiply the derivative of pre, right, remember from the previous step we said with respect to pre, and then we're going to say the derivative of pre with respect to this output, right, so it's the same thing, and then multiplied by the derivative of this output with respect to weight 1, right, so we are moving backwards, hence that is why it's called the back propagation. So this is how it's done: derivative of the cost function with respect to pre, and then the derivative of pre with respect to output 1, and then the derivative of output 1 with respect to W1. So we are moving backward until we get to that weight we want to change. So considering this last expression, this last term of the product, right, we end up having this right here, because as you remember that this mu, as you can see, we have mu1 is because of this summation, right? You remember there are two processes that are taking place within this node, right, for linearization and non-linearization, right? But then in this case we're gonna consider mu, right? So as you can see, so we're gonna derive, so we're gonna expand this expression, right, this partial derivative. So how are we going to expand it? We are going to say that the derivative of output 1 with respect to, because we cannot directly get to weight 1, it's the same issue that we had initially. So we're going to say the derivative of output 1 with respect to the summation, and then we say the summation with respect, we're going to say the partial derivative of the summation with respect to weight 1, right? That's the only way for us to get to weight 1, because weight 1 is embedded within mu1. So it's better for us to expand this partial derivative, and then when we get here we are going to expand. This is our updated partial derivative, and then considering weight 1 we have this, right? So this is the product, right? If you look at the left hand side, we have a product which is composed of 4 partial derivatives. So in this slide, what I'm trying to explain here is what does each partial derivative, like what value does each partial derivative has, right? So we're going to start with the first partial derivative of the product. We are having this one, remember, this comes from the cost function. Then we are having weight 7. So if we derive pre with respect to to P1, we see that P1 is the only, weight 7 is the variable in this case, and the rest are constants. So if we derive this with respect to weight 7, if we derive this with respect to P1, then we are going to be left with weight 7. And then we come to the next partial derivative. So we know that if you derive, remember P1 is the sigmoid, function. If you derive the sigmoid function with respect to mu1, what you get is this P1 multiplied by 1 minus P1, right? Given that P1 is this sigmoid function, right? So here you will have to use calculus, right? You can try it out and check. So then this is the answer, and then we go to the last one, to the last component, to the last partial derivative of the product, right? So what we are going to be left with is x1, because the rest are constant. Only x1 is the only weight 1 is the variable. So if we derive this expression, we are going to be left with only x1, right? And then now it's time for we put all those expressions I just explained above right now, we put them this way, and then we go ahead and substitute, and then this is what we get 0, because of, as you can see, the sigmoids. If you look at the square brackets, right, remember this sigmoid, sorry, I made a mistake there, it's supposed to be negative. Make sure that you put negative 77.41. I forgot to put a negative sign there, but if you put a negative sign there, you will realize that this is going to be 0, right? This is going to give us 0 because it's going to be 1 minus 1, and this is called gradient. So this is the problem that we have when we are using sigmoid function, and sigmoid functions are not the best. You know, when it comes to back propagation, they are not the best because of this problem, right? Because the gradient disappears. So updating weights and biases, so we're gonna use the same methods that we used previously. So right here we're just gonna replace with that 0 we just got here. We're gonna replace there, and then we have the learning rate, eta, and then we have the current weight. So what we're gonna get, since this is 0 and it's going to be 0 for all other weights, right? Because of this is gonna occur in every weight, in every partial derivative that we are going to try to compute. This is going to appear, right? Thus so what we are going to do now, we are going to substitute, right? So we know the current weight, it's 0,4 minus the learning rate multiplied by the gradient. As we saw that our gradient was 0, so the value does not change. The 0 in the expression will affect every weight and bias in the first stage, and thus we have all these weights in the first stage, right? So you remember in this stage we have those weights. They are not going to change, because you remember that sigmoid function. So you remember that sigmoid function, there is that expression. This expression, if this expression within the square brackets is going to appear in every weight that we are going to in a gradient of every weight that we are going to try to compute, right? This expression, that value is going to affect the weights. It's going to affect them to not change, right? As you can see, the only values that will change after we have performed one pass, right? After we have performed one pass, only these values are going to update, to change, and this one. But then these ones, they are not going to change because of that 0. And then, so this method is actually called stochastic descent, gradient descent. So now we finally completed one pass of forward and backward propagation using data from the first row of our data set. So what's going to happen? The next step is to input data in the second row using the updated weights and biases, right, from the previous pass, from the previous pass. So we're going to use these values, these weights. The only thing that's going to change, we're going to change the inputs here, the second row, but using the updated weights from the previous pass, right? So, and then perform forward and backward propagation to update the weights. Using those weights and biases, we're gonna perform forward propagation. And what's the purpose of performing forward propagation? Is to get a cost function. So once we got that cost function, we're gonna perform backward propagation to minimize that cost function, right? Is the same steps, right? So we do this process for next rows of the data set, using the entire data set once in performing forward and backward propagation, that is called an epoch, right? So in our case, we have 4 rows, right? So let me just go back to the first slide. Let me just. So we are having 3 rows, right? So once we have performed forward and backward propagation for each row, once that those processes are done for this row, for this data, training data, we call that a epoch, right? So what are other concepts to consider? How large, one of the questions you need to ask yourself are how large the learning rate should be. Is stochastic gradient descent the best way? Are there any ways? What about different types of nonlinear activation functions? Remember, in our case, we chose the sigmoid function. What about initial values for the weights and biases? Remember, in our case, we use random values. When do we know when to stop training the neural network? So we need to also know that since we have trained our model, what about testing our model, right? In this case, so far we only discussed how to train our model, right? So what are other concepts to consider? The learning rate is the most important parameter to tune, right? So this is very important. The learning rate is the most important parameter to change, actually. And then we have, besides stochastic gradient descent, we can use what we call the batch gradient descent by using the whole columns to update weights and biases by forward and back propagation instead of using one at a time. We also have a method called mini batch, right? So this method, which is called the batch gradient descent, we only have to use everything at once, not like the stochastic. You remember the stochastic, we have to compute cost function for each row and update the weights forward and backward for each row. But then with the batch gradient descent, we are going to use all rows and columns, right? We're going to use all of them in order to compute, to update the weights and biases, right? But we still want to perform forward and backward propagation. And then mini batch is another method which is between stochastic and the batch gradient descent. For the activation functions, we selected the sigmoid function. These are not the best because of the vanishing gradient. You remember that zero we encountered, right? So once we encounter that zero, these values, they are not updating, right? So that's one of the reasons sigmoid function is not the best option, right? And then beta activation functions are tan H and rectified linear unit functions, right? If you have came across machine learning concepts, you will come across these functions. What are other concepts to consider? You have to randomize the initial weights and biases, right? Training involves multiple epochs where the cost function is reduced to a minimum, right? So I heard that this is not always the case, right? Sometimes the cost function tends to increase, right? So if you're lucky, the cost function will keep on decreasing, right? So remember, the cost function is made up of the difference between the predicted value and the actual value. So if that decreases, becomes smaller, that means we are doing great, right? Therefore, we stop training when the error from the cost function hardly changes, right? So once as we are training our model and it turns out that the error function does not change, or it changes like with very small variations, that is when we know that we have to stop, right? To test our model, we need to input test data that the model did not come across previously. If our model does not perform well on this test data set, then it has overfed the training data. This is very important, guys. So this is the example. So we have previously we have trained our model using the data set in the first three columns, right? As you can see right here, column 1, 2, row 1, 2, and 3. There we use them to actually test, to train. Sorry about that. To train our model, and then we're gonna use this new data set, right, to check if how our model is going to perform, right? So we're gonna see from the test data, right? So if we put these inputs, these three inputs, are they gonna into our model, are they gonna give us a minimum error? So that's the idea behind that explanation, right? So yes guys, this is the end. I think this is the end. So yeah, this is all. This is not all. You can do more research about it, right? But most of the things are covered here, right? So this is a really interesting actually, you know. So yeah guys, this is the end of the tutorial section session, I mean. So I'll see you on the next one.